Okay, great. Give me one more minute. Sorry. Okay, so yeah, the plus addition is component-wise addition mod 2. So that is, I mean to say, A1, A2 up to AN plus B1, B2 up to Bn is A1 plus B1 mod 2, so on. I mean, maybe I should not keep saying mod 2, just always use these as mod 2 rather, but okay, let me just write it this way anyway. Mod 2. This operation is also called XOR, by the way. This thing is also called A1 XOR B1. XOR means exclusive OR, so it's one if and only if exactly one of them is true. So that's the logic behind the name. And scalar multiplication is defined as so since the only scalars allowed are 0 and 1, we're working in the field F2, which just contains two elements, 0 and 1. 0 times any element V in this is just a 0 vector, which is just all zeros, and 1 times V is just V itself, right? So in this, what does linear independence? So what does linear dependence mean here? Dependence. Recall the definition. We need so V1, V2, etc. up to Vn are linearly dependent if there exists lambda 1 up to lambda n in 0, 1, because that's the only scalars that we permit, not all 0, such that lambda 1 v1 plus up to lambda n vn is 0. But note that since each lambda I is 0 or 1, we can just sort of remove the vectors that have a 0 coefficient and retain the ones that have a 1 coefficient. So this is just saying that there exists a non-empty subset of the set of naturals up to n such that the sum of the vectors corresponding to the indices that are present in S, that is summation I belonging to SVI, is 0. Basically, as long as there's a non-empty subset of vectors that sum to 0, these are linearly dependent. And so linearly independent would mean that all 2 to the n sums are distinct, right? So this implies that linearly, well, okay, so V1 up to Vn are linearly independent if summation I belonging to SVI is okay. Okay, so the map that sends S to its corresponding sum is 1, 1. Because if there's some two subsets that have the same sum. For example, if you have V1 plus V2 plus V4 equal to V2 plus V3 plus V5, then first of all, note that we can remove this, and note that minus of V3 is just the same as V3 in the sense that this is really the same as saying that the sum of all of them is 0. Because notice that that from plus we have that any vector added to itself gives the zero vector because of how addition is defined. So, and then this is a contradiction to the two linear independence. I mean, so this would make them linearly dependent. And then the converse is also true. Like if this is 1, 1, then this has to be linearly independent because the empty set and that corresponding set are distinct, right? So there's no subset that sums to 0 because then the empty set and that set would both map to the 0 vector. So this is over all subsets, not just the empty set. Okay.
This summation I belongs to S goes over like all INS or like some INS.
All INS and this S, so it's a function from the power set of n. I mean, it's function from the power set of up to n to f to n, defined as f of s is equal to this. Basically, I'm just taking all possible subset combination sums, and I'm saying that they must all be distinct for linear independence, and it's enough. Like for example, if n is 2, then I'm saying that the 0 vector v1, v2, and v1 plus v2 are distinct if if and only if v1 and v2 are linearly independent. 4 distinct sums. Is that clear?
Yeah.
Okay. So I'm just taking all possible subsets and then finding the sum. And I'm saying that they must all be distinct. And in fact, they're distinct if and only if the vectors are linearly independent. So now note that, so basically, it all connects in the sense that the basis of, so basically if I have a vector space, which is a subspace of this, then, and the dimension of V is M, that is I have M linearly independent vectors, then the size of V is 2 to the M. Because those M vectors in the basis must, first of all possible sums of them span the entire vector space V, and there are 2 to the M distinct ones. All the corresponding sums are distinct because they're linearly independent. So we get this.
Can you just repeat the part where it is 2 to the M?
Yes. So if the dimension of V is M, then notice that V is the span of some subset of M linearly independent vectors, right?
Yes.
So, and these are linearly independent. And first of all, how many distinct combinations can you even make with these? Only 2 to the M.
2 to the M, yes.
So that's an upper bound on V, right? Because because the number of different possible combinations itself is 2 to the M. But it's also equality because all of them are distinct because of this. So
What do you mean by all of them are distinct?
So basically, if I take, so if M is 3, for example, then all of the linear combinations, this, all 8 linear combinations are distinct. No two can be equal.
Yes.
And there are literally no other combinations that I can even make. So it's exactly 2 to the M. Right? I mean, okay, so these are 8 different vectors in V, right? So then I get, okay, so if these are M vectors, then all 2 to the M linear combinations are distinct because they're linearly independent. So I get this, right? Is that clear? V is a vector space, by the way.
Yes, this is clear.
And it's also an upper bound because what other vectors can you even make?
Yes, because if it is greater than 2 to the M, then like we will have another linearly independent vector,
Yes.
which is just in contradiction.
Yes. Or you can notice that since this is the span of these vectors, it means any vector in V is a linear combination of these. And so I've already counted them here. Right?
Yes.
And so we get equality. Okay. So we have some,
Like, but if some linear combination is equal to another, then we get that these bunch of linear vectors are linearly dependent, which is the same contradiction, right?
yes,
So
because
so they can't be equal. Yes, I got it.
yes, they can't be. Yeah, we need the fact that these are linearly independent as well. Yeah, this is important. So we get this upper bound, we get this lower bound because of linear independence. We get this upper bound because it spans the entire vector space. I mean, if you take any m vectors, even if they're not linearly independent, you can only make 2 to the m different vectors out of them. So which is why this is an upper bound, and yeah, just reminder. Okay, fine. So okay, so this was just a small summary. We get back to this problem now. We start doing the problems again. So yeah, this is our question. So since we already know this would use linear algebra and we have this red-blue hint, the idea is to consider each edge as like a bit in the, I mean, so consider an
Like you
M
will
tuple.
try to introduce that to the an idea here.
Yes, somewhere we want to use this everything, this whole concept that we've learned. So the idea is to consider F2M. So it contains, so what does this contain? It contains these sort of tuples we know, where each AI is 0 or 1. And to each, so for every configuration, there's a very natural correspondence here, right? So for example, if my edges are E1, E2 up to EM, so if this is red, then then consider a 0 in that tuple. Right? And if this is red, then another 0. And if this is blue, then there's a 1 here. So whatever. So there's a very natural correspondence between the 2 to the m different edge colorings and like this set, right? And now what does the operation really do?
It just switches like it. We do an operation on HB, then it just switches the number on the
Yes, but we are doing operations
edges.
on vertices, not
Yes,
edges. Yeah.
but and like if some edges join to V, that edge color also changes, right?
And so what is that operation? Like exactly what are we doing?
Like we are adding in some
Yes,
way.
exactly. Exactly. So we are, so each operation corresponds to addition actually. Corresponds to addition. How exactly? Because if, for example, if I have 5 edges, let's say A1, 5, and suppose there's a vertex that that such that edges 1, 3, and 4 are incident on it. Right? So then performing this operation and changing the color of each edge incident on that vertex just corresponds to adding this. Because this is what switches it. Adding 1 would switch 0 to 1 and 1 to 0. So yeah, so that's right. And then what? So the first step should be to try and formulate the entire thing as a linear algebra problem, right? So then, okay, so we've made this observation. What now?
But then
You can kind of reverse the operation. So you can start from all zeros and you want to reach any configuration, or its complement.
Yes, you're right. Yes, you're right. Yeah. Or you could also say that starting from any vector, prove that starting from anything, prove that there's a V such that you can reach neither V or minus V. That is complement of V. That's also one way to do it. But yeah, what you said is also right. So okay, first of all, let's formulate this problem, right? What does it mean to choose V and change the color, right? So we have n vertices. So they correspond to n vectors, right? N vectors.
yes, sir.
Let's say, so I don't want to use V.
And in each step we like just change the color of one vector.
Yes. So basically, what we are doing is we start with some vector V, some vector W, and well, okay, I don't want to use W. Let's say U, and uh, and in each step we add one of the WIs, right? Add some WI to U. Oh, to U. We want to prove that there exists a U such that we can never reach zero, 1. I mean, by here, okay, yeah, this is fine. We can reach neither 0 nor 1. That just makes it clearer. Reach neither the 0 vector nor the 1 vector. Right. Okay. So what's the way to do this?
These n vectors can span at most 2 to the n things.
Correct. That's right. Because we have this U. First of all, note that adding the same vector twice just cancels out, right? So it doesn't. Oh. Hold on. Yeah. Okay. So first of all, note that adding the same vector doesn't do anything. So because the adding just commutes and just WI plus WI 0. So the only thing we need to consider is this set, right? So sort of U plus summation INS W I, where S is a subset of the set of n natural numbers. Basically, just all possible sums here added to U. We want to show that there is a U such that we reach neither 0 nor 1. And so the first observation made was that note that the cardinality of this is at most 2 to the n. 2 to the n, yes. Because we can only have 2 to the n different things here, right? Okay. What else can be said?
So essentially, we want u to choose u such that neither u nor 1 minus u is in this span.
Neither
So-
0 nor 1 is in the span.
No, I'm considering this span to be summation of wi.
Yes. So,
Like
yes.
the vectors, span of the vectors.
Yes.
No?
Yes.
Yeah.
We want to show that there exists a vector. So this u doesn't even make sense. We just want to show that there exists a u such that u does not belong to this sort of set summation. So u is not equal to any of the wi summations, and it's also not equal to like the complement of u.
So if m is greater than n plus 1, then this is
Why?
Because like if
each
it
of
like
those is true to the
contains
n.
each pair, then it has to contain half of the number of u, which is at least true to the n, I think.
So if it's strictly greater, then we're done, right?
Oh, right.
We still need to work out the case where m is equal to n plus 1. Yeah, you're right. So the point is that if this were not true, if not true, then notice that for each vector, so for each vector and its complement, one of them is in this sort of a representation. And so then summation I belonging to SWI over all S would must cover at least half the total number of elements in this set, right? In this, because if you're saying that this is not true, then for each vector and its complement, one of them must be representable as the summation of wi. So it must cover at least these many elements. But note that we know that this covers at most 2 to the n elements. Then this would mean n is less than equal to n plus 1. So if m is greater than n plus 1, we have a contradiction. We are already done. So only need to consider the case where m is equal to n plus 1.
If m is equal to n plus 1, then the cardinality of that set is 2 to the n, right? Which is just
Yeah, which is,
wait no.
I mean, that's not a contradiction.
You can assume graph is connected, then delete all leaves.
I mean, I guess, yeah, I mean, sure. Wait. I mean, sure. Okay, let's assume the graph is connected.
And if we delete all leaves, then this means that the graph is just 2 cycles connected.
No, so why is that true?
If you pick the largest cycle, then like if there's
Oh, you're deleting the largest cycle, you said.
no, deleting all leaves.
All these, but what about something like this?
Yeah, this is 2 cycles connected.
Two. Okay, I see. Yeah, you're right. Yeah, I guess. Yeah. Yes. Yeah. Okay. Can they be vertex connected as well? I think so. Yeah. Even this is fine, I think.
Yeah, either edge or vertex.
Yeah.
It's like we can just do it by hand or something.
Yeah, but I don't want. I mean, I want to fixate on a linear, like completely algebraic argument because there is one.
Okay.
Yeah, I think combinatorially it shouldn't be too complicated to think about two cycles. Like, I mean, how bad can it be really? But yeah, I mean, there is a linear algebraic argument. So think about this part.
Well, that says the vectors are linearly independent
Yes,
because this must be tight.
yes,
So you can't like return to the same configuration again. That's
Yes.
what it says.
yes.
Uh,
But
but
can we?
then-
But we can just like add wi again.
No, that's not allowed. I mean, I mean, I'm just considering these distinct subset combinations, right?
Okay.
So yeah.
but is it necessary that we make non-zero moves?
No, not necessarily.
Okay. Because one is also not in the span of these vectors because exactly one of u and one minus u is in the span.
Correct.
So if 0 is not in the span, 1 is not in the span.
Yeah, but 0 is in the span, right? Because
Oh
that's-
yeah, because you're not adding anything. Only then. But for non-NP subsets,
for non-empty, neither 0 nor 1 is in the span. Sure. You're
yeah.
right. Because of the yeah. So okay. So I'm trying to make you think about this. So I'm trying to make you think about the WI more carefully.
Wait, actually, how did we get 2 to the m minus 1?
Oh, we said that. So to con so so if we assume the contrary, then these sums must cover exactly at least one of a vector and its complement. Because if there is a u such that neither u nor 1 minus u is of this form, then that u works. Right? And so if we are assuming the contrary, then we are saying that for each vector and its complement sort of paired together. By complement, I mean just flip the bits. At least one of them must be representable as summation wi for some subset of indices. And so since the entire vector space has 2 to the m elements, so we must cover at least 2 to the m minus 1 elements using these summations. But then there are only n such vectors, so we can have at most 2 to the n such summations. And so 2 to the n is at least 2 to the m minus 1.
No, like, why did we divide by 2?
Because
Because it should either like contain the complement or like u.
we can only say that one of these, well, at least one of these should be covered, right? assuming a quantity, which is why we divided by 2. So for so we can divide the set of all 2 to the m vectors in this, in f to m, into 2 to the m minus 1 pairs, right? Where u gets paired up with 1 minus u. And I'm saying that for each pair, one of these must be representable as summation wi.
Right, right.
And so at least 2 to the m minus 1 vectors must be representable as summation wi.
Yeah, got it.
So okay, so right now, where are we? We are at this stage where we're focusing on m is equal to n plus 1, because we already have a contradiction for m strictly more. And it must be the case that 2 to the n is the cardinality of all these sort of different summations. Which is really the same as saying, what is it the same as saying? What does it mean for the
That they are
sum?
linearly independent.
Yes. Are linearly independent. And we must also have this covering thing. The question is, are they linearly independent?
I guess no, because like we can just get a combination of W1, W2, and Wn such that they are equal to 0.
What combination?
Like, because if it isn't equal to 0, then we can change the lambda to 0 and get that it is equal to 0 then.
I don't understand.
Like, for the sake of contradiction, assume that they are linearly independent.
Okay.
Then if they are linearly independent, then all these W1, W2, and Wn were defined to be 0 and 1, right?
Wi is a vector. They're not zeros and ones.
Oh.
So,
But they should.
so this is like a W1, right? This is a W1. W1 itself is like a tuple. I'm just making
Yes.
sure it's clear.
Okay, then if we prove that, we can get a combination of linear combination of W1, W2, and Wn such that it is congruent to 0 modulo 2, then we would be done, right?
Not congruent, equal to the 0 vector, like the 5 tuple 0, 0, 0, 0, 0.
Yes.
Yes, you're right. Sure.
But then if it isn't, then we get that this sum is equal to some non-zero congruent mod. Wait, no. It doesn't make sense.
Yeah. Just want to make sure if this is clear. These Wi's correspond to the vertices, and so let's say W1 correspond to the first vertex, and if you make that operation on the first vertex, it's like adding the vector W1 to u being the current configuration.
Oh, right. If you add all the vectors, they must add up to 0, because if you toggle all of the vertices, W1 plus W2 plus Wn is 0.
Good. Exactly. Nice. That's the whole point, right? If you switch all vertices, then you do nothing.
Oh, yes.
Because each edge has 2 vertices at its endpoints. So actually W1 plus W2 plus up to Wn is 0. Which is the same as saying, notice in the problem, if I choose each vertex exactly once and change the color, then nothing happens because each edge gets switched twice. Right? And so this sum is actually 0, which means this is not a linearly independent set. This is not linearly independent.
Like if we switch the color of an vertex, then the color of the edge changes twice. So then there is no change, right?
Yes, exactly. So
it is an invariant, right? This sum, it remains 0 only.
Is this sum W1 plus W2 plus up to Wn is always 0? Yes. So the point is that this is not linearly independent. So what can we say about the size of this set now?
It is smaller than 2 to the n.
But actually, can you be, I mean, it's just smaller is enough, but can you be more precise?
Like if it isn't like linearly independent, then we can just take its span, and the span should be like linearly
2 to the n
independent.
minus 1.
Yes.
In fact, we can also say this, right? Because
yes,
this
yes.
is a vector space.
But just because like its span will have an dimension in minus 1.
Or smaller, yes.
Yes, yes.
Yeah.
So it
you're
is
right.
smaller than 2 to the n.
Yeah.
Yes,
If
yes.
strictly smaller than 2 to the n is enough. But the point is that now we know that this is at most 2 to the n minus 1. And if we had assumed the contrary, then this would have been at least 2 to the m minus 1, which would mean that m is at most n, which is a contradiction. Or if you want to just rethink the entire thing and saying that these sort of combinations can only give us these many vectors, but the total number of vectors is 2 to the n, which is at least 4 times 2 to the n minus 1. And so there is at least one vector and its complement which are both not representable, because otherwise half the vectors would be representable. Yes, so that finishes the problem. So just as an example, if m is 6 and n is 5, then I'm saying that these 5 vertices, if you try to switch them, these can only give me 16 different colorings. But these correspond to like 64 different colorings. So that would lead me to this sort of.
So like there is some set that like the intersection is something smaller than this one.
Well, I'm
I'm
saying
just
that,
lacking words.
yeah, I'm saying that there is a V and a 1 minus V. Basically, there is a configuration C and its complement configuration, which are both not in this.
Yes, yes.
And then this, if you take this to be the initial configuration, then you cannot reach 0, because if C plus some combination here reaches 0, then this combination itself would be C, which is a contradiction, because I'm saying that C is not representable as a C is not one of these 16 different colorings. And if C plus one of these 16 different colorings reaches all blues, which is 1, then this 16 different colorings would correspond to the complement of C, which again, I'm saying by choice of C is a contradiction. So this C works. Yeah, so there was one sort of combinatorial observation that you needed to extract from the original problem, that the sum of these is 0. So I mean, it was a little deceptive that I just converted it to an algebra problem and forgot about this, because it's important that these vectors can't be anything. This particularly correspond to vertices. So if instead of vertices, I could have made this switch with any sort of subsets, then this problem is actually not true. Very particular that each edge is incident on exactly 2 vertices, so that the sum of all the vectors is 0. Okay. Let's do another problem. Hmm. Okay. So let n be a natural and a1, a2 up to an plus 1 be a non-empty subsets of 1, 2, so on up to n. Prove that there exists two disjoint non-empty subsets. Copying this from AOPS actually. Looks a little ridiculous at first, but so okay, let me just phrase this problem more easily. So the point, okay, so we have n plus 1 non-empty subsets of this set. We want to show that, so let's say n is 5, for example. We want to show that there is some subset, this one subset like this, and then another corresponding to, let's say, this and this, for example, such that the union of these is the same as the union of these. So we want to circle some of these sets and square out some of these sets such that no set is both squared and circled, and then at least one circle, at least one square, and the union of the set squared, as in squared, is the union of the set circled. That's what it's trying to say.
Because there are n plus 1 things, we can find some subset that adds to 0, the 0 vector. As in some combination of these AI will have that every element occurs an even number of times.
Right. Wait. Yes.
Like if we get that 2,
Yes, you're right.
can we just try to denote these subsets by vectors? It would be nice.
Yeah, you could do that.
If we have this, then we get that A1 like those some elements in this non-empty subsets of n plus 1 is has some zero, so it means like a1 a2 an plus 1. If we prove that it is linearly independent, then I guess we can do linearly dependent.
The problem is that since this is a union, it's not that convenient to think of these as adding vectors directly, because if there's a 1 in this and a 1 in this, and then there's no ones here, then
Yes, yes.
it's not like adding them should correspond to a 0 in that case. It should correspond to a 1.
But like, can we just subtract into that these AI1, AI2 and till AIK are distant? But like then it would put a restriction on the n plus n subsets.
Yeah, I mean, you cannot just
Yes.
take,
That would be yes.
you could have these subsets that are no to a different.
We could do bitwise or though.
But does that correspond to union? As in, okay, so yes, we could bitwise or. Yes, you're right. That union is a bitwise or, yes. Yeah. But or doesn't exactly correspond to addition, unfortunately. So. But you're right. We could bitwise or. Yeah.
Wait, so can we like define the vector space in terms of like or instead of normal addition?
We cannot because then
Unions in the problem, like we need to do something with union.
yeah, but it's a good question, but the problem is that, for example, if you add anything to the one vector, then it will always give me. So he's saying that if can we somehow modify this, and instead of plus we can get an or. So for example, can we modify it and get this sort of a thing? Then it would work perfectly for our purpose. The problem is that
Yes,
notice-
then we would need to prove that some subset of these n plus n subsets are linearly independent, which is just easy to prove, I guess.
yes, yeah, but the problem is that this is not a correct vector space, because notice that this happens and this actually forces B to be 0, because in sort of vector spaces A plus B equal to C implies, if I add, okay, so okay, well, that's not exactly how I wanted to frame it, but addition in vector spaces does not work that way, because there are certain rules for addition and for
Yes,
all
that's
this,
a
everything
line
to make
that's
sense.
vector space only.
So
Can
yeah,
you like summarize those rules? Like this is the basic.
yes.
Isn't the issue here that one doesn't have an inverse in bitwise or?
Yeah, one doesn't have it. Well, I mean, the identity well, what even is the identity element here? So
Or yeah,
Zero,
well, I
right?
guess all zeros must be the identity element, right? Yeah, but yes, it has to be. But then, yeah, one doesn't have an inverse. There is no vector which, when added to, in fact, there's no element that has an inverse other than 0 itself, right?
no, as in it's not a field. Like bitwise or doesn't define a field.
Yes, yes, exactly. That's the problem. So,
All right.
but okay, just do this and I'll just summarize the rules after this. Why
Like,
not?
is the idea to generalize this union into some sum of elements in these n plus n subsets?
Yeah, I want to view these unions as sums. You're right.
Yeah.
But you have to be careful, because if you take f2n, then 1 plus 1 becomes 0, and then you can't distinguish it from absence of that element.
Yes, sir.
So yeah.
So there are like 2 to the n plus 1 possible ways we can take subsets of 1 to n plus 1.
Correct.
So each of these corresponds to, say, a subset of 1 to n, because we are taking those indices and like taking their union. But that's not an injective, that can't be an injective function. So sum 2 must correspond to the same union. And then we can delete common elements.
That's the problem. If you delete, then there's an issue. Because for example, if you have something like this, you're right that there will be some unions that are the same. For example, that is just sort of pigeonhole principle or something. But suppose 1 is in all of these, but 1 is not here. And if you delete A2, A3,
Oh,
now in this 1 is here, but 1 is not here. So that's an issue. But good try. That's the first thing that came into my mind is like, but this naturally doesn't work. Yeah. Well, to say it formally, a vector space is defined over a field. Well, vector space. Well, I don't want to get into what a field is, but some examples of fields that you know are like reals with its normal addition and multiplication, or even rationals with multiplication and addition, the natural ones. And then Z prime with, so this is like mod P, and then multiplication is done. So you can also define multiplication mod P, and then every non-zero element has a multiplicative inverse. So a particular case would be Z2, where we have 0 and 1, and addition, note that addition here is like mod. So addition here is just the XOR operation that I was talking about, and multiplication is, well, 1 into 1 is 1, 1 into 0 is 0, etc. It's the AND operation. And so it's some set V along with two binary operations called addition of vectors and then scalar multiplication. So addition of vectors is such that is between two vectors, and it's commutative, associative. There must be an identity element, which is there must be a vector then added to any vector just gives me back the vector. So V plus 0 is V. And then I should also have an inverse, which is for every vector V, there should be another vector which when added to V becomes 0. And then we should also have scalar multiplication properties. For example, well, scalar multiplication is, well, okay. So we have these sort of properties that this should be equal to AB times B. But A is an element of the field, AB. So this product is not defined between two vectors. We define it as a scalar multiplied by a vector. For example, like 2 times the vector 1, 1, 1 in like real space gives me 2, 2, 2. I don't define product of two vectors. So this is A, B are in the field, and B is a vector. And I'm just reading it off the page because I might miss rules, so it's just better to just write them correctly than to miss it. Where 1 is the identity element, and then I have AU plus B is AU plus AV, and A plus BV is AV plus PV, these sort of rules. So the issue why OR doesn't work is because of this inverse thing. The identity is all zeros, right? Because so what the idea was, just to make sure everyone gets it, is that if I could define plus as the OR operation, that is, I could do this, then notice that in this question set, unions would make so much sense. For example, if I have this set 1, 2, 3 and another set 1, 4, 5, and let's say n is 5, then this corresponds to like a vector 1, 1, 1, 0, 0. This corresponds to 1, 0, 0, 1, 1, right? But the ith element is 1 if that I is in that set. But if I just do the XOR operation and take a union here, I'll get 1, 2, 3, 4, 5 is 0, 1, 1, 1, 1. But that's not good because I still want this to be a 1. So if I could have a vector space where 1 plus 1 becomes a 1, then this would be perfect. The issue is that this is not a vector space because we don't have an inverse for every vector. Because there is no other vector which can give me 0. Because once there's if V is not 0, because if there's a 1 in some position, then no matter what I do in that position, it will remain a 1. And so this is not a vector space. So yeah. That was just a quick saying of why that idea doesn't work. Okay.
I guess if we find some way to convert this into addition, then this problem has like no other thing to be done.
Right. Right. Yeah.
But do we really do it, or there is another way?
What do you mean? Like,
Like,
no,
do we
I mean,
really convert it
we're,
to some?
we're not just trying to discover new vector spaces where we could make sense of union. So that's not what we're trying to do.
Okay.
Union probably can never make sense, right? Because of that same issue. Like the null set is always
There is the
an identity.
inverse issue, I guess.
Yeah, the inverse issue will exist. Don't want to make it formal, but yeah, I guess that's always an issue. Yeah.
I guess then there would be some two subsets that are equal in A1 to n plus 1.
Equivalent to what?
Like if there are two equivalent to each other, like a size argument would work with the I1 I2k argument.
I'm not sure what you mean. Can you see that once more?
Where
Oh, yeah, there was. Just a minute. Yes, I'm back. So yes, it's very natural to write each AI to 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 make a correspondence of each AI with a vector vi, which is like ones and zeros corresponding to where, like, it's basically shouldn't use A1. It's fine. Well, AI1 to AIN, where Aij is 1 if J belongs to the set, and 0 if J does not belong to the set, right? For instance, 137 would be 101.67, whatever the total number of elements is, all zeros. And we have n plus 1 such vectors.
I guess we have that they are linearly dependent.
In what space? F2n, right? I mean F2.
Yes, it's F2n.
Right.
Bitwise in bitwise.
Right, because there are n plus 1 such vectors, and
Like these I1, I2 then would repeat to each other and map to each other, and since you sum them, so they become all like 0, 0, 0, 0, 0.
okay.
So we have that this A1, A2, An plus 1 is linearly dependent in F2n. Then like
Wait, what was your previous statement?
what?
Basically, these are n plus 1 vectors in a space of dimension n, so they're linearly
Yes.
dependent. Yes.
I'm saying dependent, not independent.
Yes, yeah, they're dependent. Yes.
So if you find like two disjoint subsets such that they are linearly linearly dependent, then I guess those subsets would work
Why?
for the values of I1, I2, Ik. Like because then AI1 union AI2 till AIK is smaller than or equal to the sum AI1, AI2, AIK.
What does that mean? Smaller
Then
than equal to. These are sets, right?
because of pi, I guess, principle of inclusion and exclusion.
No, wait. Oh, you're saying cardinalities.
Yes,
Oh,
yes, cardinality.
okay. Even if we get equal cardinalities, what does that mean?
Like if the cardinality is 0, then they are surely equal.
Yeah, but cardinality is not 0.
Oh, yes.
You can't add cardinalities mod 2, right? I mean,
Yes, yes, we are.
so okay. So to give you a nudge, don't think about F2n. Just think about R to the n. Just n-dimensional Euclidean space, just regular R to the n that we covered last time. But we can basically our usual vectors, right? Like for example, 101 plus 110 will be 211. Right? Nothing fancy.
Right. So if you have some linear dependence over r to the n of these vectors,
Yes.
and then you take the positive coefficient ones and the negative coefficient ones. So the positive, like you have to say these vectors are v1, v2, vn.
So yeah. So let's say these vectors are.
Wait, are these linearly dependent in the n-dimensional Euclidean plane?
Yeah,
Oh,
because the
sorry.
dimension of r to the n is n, right? We have n plus one vector.
Oh, yes, yes, makes sense. Okay.
So these are linearly dependent.
Yes.
Yeah. So sorry, you were saying.
Yeah,
guess I-
so whatever is included in the union of the positive coefficient ones must also be included in the coefficient of the negative coefficient ones. Otherwise, it can't cancel or and become zero. So they
Yeah.
have the same union.
Yeah, that's it. That is the solution. Yeah. So
Like proving linear dependence was the main part.
I mean, this is just clear, right? I mean,
Yes.
you don't need to prove it.
I was just like stuck on prove linear dependence now.
Well, so
I
for
didn't
example,
notice this at all.
it's fine. I mean, so for example, if this is just to make sure, for example, if I have, so since these are linearly dependent, there is some subset of these vectors that sum to zero, like non-empty subset with some coefficients that are non-zero that sum to zero, right? So for example, I have this. Let's say I have this, right? And so what you do is you keep the positive coefficients on one side and the negative coefficients on one side. And the claim is that A1 union A3 is equal to A2 union A4. And why is that?
Because if it isn't, then how would they cancel?
Exactly. Because if there's some element here which is not here, then the corresponding, so if the element is j which is not here, then look at the jth component of this vector, right? Here it would be positive because these vectors are ones and zeros only, right? So if there's a j in A1, for example, then this would have a 1 in that position. If the j was in A3, then there would be a 4 in that position. And if the j is in both, there would be a 5 in that position, right? So,
Yes.
so the position where j is would be non-zero here. But if j is not in the RHS, then the position of j there would be 0. And so these cannot be equal. So any element which is in on one side is also in the other side, vice versa. And so these unions are actually equal. That's it.
What is the source of this problem?
I think this is China TST. Let me see. No, this is China Western MO 2002. It's an old book.
Okay.
Yeah. But yeah, I mean,
Can
that's
you
it.
just like share a pile of problems on linear combi using linear
Yes, I'm
algebra?
writing I'm just putting everything into LaTeX. I'm just too lazy.
I guess because I just feel that it's really nice.
Yeah, it's really nice. There's so many problems here. I could just compile all of them. There's like a whole 250-page book on linear algebra.
Like whole combi is just converted into some algebra argument.
Yeah, it's really good. Yeah. So let's just try one more problem and then we'll discuss. Don't want to use up all problems because then there'll be nothing to do. So you wait. The more I can cover linear algebra, the more combinatorial problems also we can discuss, because there's a lot of these combinatorial problems that require like matrices and knowledge of ranks and nullity, etc. And so the more we know linear algebra, the more combinatorics we can do. But
So
that's
are you
fine.
planning for a third session?
Well, no, I mean we don't have time. But
Like, can we just cover it in this? Just like elongate it a bit.
let's discuss that offline.
Okay.
Let's do one more problem. And there are also problems related to eigenvalues that are really good. Yeah, those are also nice. Okay, so let's try this problem. This is a little more famous. You might have seen this. Be a finite simple graph. Uh, Initially all vertices are bad at each step. We can pick a vertex V and change, well, okay, V and its neighbors to the opposite configuration. Well, actually, okay. Let's say all vertices are off. Let's say the vertices are like switches, right? So we can toggle the configuration of to the opposite of what it was. Basically, off becomes on becomes off. Prove that all vertices can be switched on. You can assume connected because you can do it for each connected component.
Can we just try to like consider the sums in between F2N?
Yeah, F2N is natural here because twice is just the
Yes,
same another.
off is equal to 0 and on is equal to 1.
Yes.
And like consider all vertices to be vectors v1, v2, vn.
Yeah.
So we need to have like some sequence of like we add opposite of vn, like if v1 is equal to 0, then we add like 1 to it.
Vector is equal to 0. What does that mean?
No, like we
Oh, the vertex is
adding,
zero.
yes, it's vertex.
Yeah.
So we need to bring like this addition thing in some way and just prove that it is like linearly dependent, then we would be done, I guess.
So like we would be done if they were independent.
Oh yes, independent.
Yes. Yeah, if they were independent, then we'd be done because then you can reach anything. But it's not that if they're not, well, I mean, well, it's not, the converse is not true. It's not true that to show the problem, you must show independence. So it's,
Yeah. Useless.
so if we prove if we can prove independence, then that would be good because that's stronger than the problem itself.
Independence is false, right? Because like, what if you have two points that are just connected to each other? Then their vectors
Yes.
would be the same.
So they're not, you're right. In fact, if every vertex has an odd degree, then the sum of all the vectors would be 0 because then
Yes,
each
yes.
vector would be flipped even number of times. Yeah.
But there are just odd number of vertices with odd degree.
Even number of vertices with odd degree.
Yes, even. Okay. I am saying that was it. Why?
Well, but okay, I'm just saying that all of them have odd degree, then it's definitely not linearly independent. For example, just an edge, a graph with just two vertices connected. If you flip both of them, you do nothing. Ideas?
I guess considering him F2N would really help.
Yeah.
And considering the sums like in the same way we did in that simple graph problem.
So F2N, and initially, since all of them are off, we start with this configuration of all zeros. And then we have these vertices, and they correspond to these vectors. Vertex V1, V2 corresponds to vector V1, V2. And so what this corresponds to is like one at its own place as well as wherever the neighbors are. And similarly for these. And I want a subset of these that subset that sums to the all ones.
It also satisfies another property like the jth position of Vi must be equal to the ith position of Vj, right?
Yes, you're right. Yeah. Wait, jth position of, yes, you're right. Yes. The jth position of,
Wait, what are V1, V2, Vn defined to be?
these are the vertices and these are the vectors correspond to the vertices that switch them on, right? So for example, if V1 is the first vertex and it's adjacent to the third and fourth vertices, then this would be 1, 0, 1, 1, 0. Let's say if there are only 5 vertices, right? Yeah. Just okay, so I should write that. Let me write that. So Bij is 1. So this corresponds to the ith vertex. So let's say that the vertices are from 1 to n, right? That's better. So Vij is 1 if j equal to I or j is the neighbor of I. Is a neighbor of I. 0 otherwise. So one property that was mentioned is that, sorry, Vij is just a scalar. One property you mentioned was that Vij is Vji. That's right. Because either I is equal to j or I and j are neighbors. And neighbors is a what is this called? Reflect, no, not reflective.
Adjacent, do you mean?
No,
Mutual.
Symmetric.
yes, symmetric. Yeah. Right. Yeah, mutual. Yeah, whatever. I was just trying to find the relation. Yeah, symmetric. Right. And of course, VII is 1. So this is sort of like, this has ones on the diagonal, and then wherever there's a, whatever is here is also here, like a reflection along this diagonal. If you know terminology from matrices, this is a symmetric matrix. If that helps. And this is actually invertible, like you don't lose any generality, like, because for any such vectors with these properties, you can make a graph, right? Because for any such vectors where Vij is Vji, for I not equal to j, and Vii is 1, you can make a graph out of that wherever, because wherever there's a 1, just make an edge. Wherever, yeah, that's it, right? Wherever there's a 1 on the off diagonal, make an edge. So we don't lose generality when we go from this graph to this, because this is exactly invertible. So here it's safe to forget about the combinatorial part if we want to. Like, we can forget about the problem and just think about these vectors if we want to. That is. This was this is different from this problem where we needed the fact that these wi sum to 0. It's not exactly reversible. So yeah. So I guess that's one thing to keep in mind, that if you can sort of reverse it and then anything here corresponds to the problem, then it's okay to forget about the combinatorial part, because it's like as hard, or both are true, whatever, equivalent. Anyway, we still have to solve the problem.
Also, we can reduce the problem to all of the vertices having odd degree, right? By inducting.
How?
Like let's say we have n vertices. You remove one vertex and you what is it? Perform the operations with those remaining n minus one vertices.
Mhm.
And since the remote vertex has an even degree, it gets on. Oh, never mind. Yeah, fine.
Yeah, the problem is we don't know how many times the neighbors will switch.
Yeah, you're right.
Let's think about it. Do we know something about it? Hmm. So right now, what have we reduced our problem to? We've reduced it to this, right? Let M be an n cross n symmetric matrix with 0, 1 entries, right? And 1 on the diagonals. Prove that there is a subset of the rows that sum to that sum to all ones in mod 2, by the way. So this is in mod 2. Okay.
Wait, so we're multiplying by a vector in some sense. Like, uh, like with each row, if we want to take it, we put a 1, and if we don't want to take it, we put a 0.
Correct.
So like it multiplies out all the, like, basically we want to show that there exists a vector such that v equals 1, 1, 1.
Well, that would be a little different, wouldn't it? Because
It's the same here because the rows and the columns are the same.
yeah,
Okay.
true. You're right. Yeah, sure. Yeah, it's the same thing. Yeah, because the first column itself is also the one. Yeah, I was thinking more of v times m equal to 1, 1, 1. But yeah, it's the same thing. Yeah, you're right. Because we can rather view these as like columns. I mean, we can also view them as subset of columns, right? So because this is also v1 because of the symmetry, because of symmetry. And now if we multiply it with basically if we multiply this matrix, we by the way for the solution we don't need to know how much matrix multiplication works, but if we multiply this with a1 a2 up to an, then what does this become? This becomes uh v1, wait, uh
No,
A-
it
wait,
rows.
A1
okay, is
V1
that
plus
right?
A2 V2 plus AN VN. Like,
No, wait, hold on. Yes, this should be 1. Yeah. This is right, isn't it? Or am I messing up?
yeah.
I think so.
Yeah, you're right. Okay, let's keep this way. But don't worry, we don't need to multiply it. It's really the same thing because these are zeros and ones. It can't be that different to interpret it differently. First of all, notice that if the rank, if these rows are linearly independent, then we are done, right? That's something we already said before. So the linearly independent, we are done. But what if they're not linearly independent?
Then we can induct down,
How?
like remove those vertices and consider the rest of the graph. Oh,
Okay.
right. There's sure that
Oh, it's
it
a good
might
idea.
affect those vertices again.
So let's say, for example, let's say let's just say there are five of these, right? And let's say these four are linearly independent, and the last row is a linear combination of the first four. So this is not linearly independent. So these are linearly independent. We can assume that by just changing rows, we can assume that the beginning k of them are linearly independent or something. So let's just say the beginning four are linearly independent and the fifth one isn't. So then what can we say? So how do we induct? So you're right. So for induction, let's say we remove this element, and so we'll have to remove something like this as well, right? So what now? Can we actually say that these are linearly independent if I just consider the first four things? Is that true?
Yeah.
Why? That was a very fast guess.
Is that because they could add to 0, but if you added their fifth coordinate, the fifth coordinate could be add up to 1.
So what are we saying? Are these linearly independent? The red part?
Well, some 4 have to be independent because their span is as size through
No, I'm
the.
specifically saying the first four. Because if I delete the V5, then I need to delete this as well. Like, so what I'm saying is I have four vectors which are linearly independent in the space where there are 5 coordinates, right? So if I drop the fifth coordinate, are they still linearly independent? That's what I'm asking.
Well, if there are odd number of ones in the last thing, then it need not be independent, right? Oh, never mind.
Well, well, okay. You're right in the sense that I can have vectors like this, two vectors that are linearly independent, but if I drop them, then these are not linearly
No,
independent.
because in fact,
But-
the part of V5, which is in the span of these 4 coordinates,
Mhm.
it has to be, it cannot be in the span of these 4 vectors. So the first 4 coordinates cannot span a linearly independent thing.
What? Wait, V5 is a linear combination of V1, V2, V3, V4, right?
Yeah.
Okay.
What was I saying?
And I'm saying that these are linearly independent when I
But
view all of
V5
the 5
has
coordinates.
coordinate 1, and if, oh no. What was I saying? Oh, sorry. That doesn't make sense.
So it's actually, okay, yeah. So it's actually not true, right? Because if let's say I take something like this. These are linearly independent. But if I drop this, then these two become equal. Okay, but this is not a symmetric example. So what about symmetric example? So okay, this is not true if I just take any vectors, right? because I can just take two of the vectors that differ in the fifth coordinate and such that these are linearly independent. And then once I drop the fifth coordinate, two of the vectors will be equal. Okay, since we're out of time, I will leave this question up to you. So I'll put this in one of the assignments, and then we can discuss this time. But just keep thinking along these lines. So it has to do with, it has a little to do with induction. Sort of basically just take k of the vectors to be linearly independent, and let's say the other n minus k are a linear combination of these. And now try to do some manipulation of the rows in some way. And yeah, okay. And you need to use symmetry somewhere. So that's one point. So this is vague, but yeah, just try it once. It's a really good problem. Yeah. Okay. Doubts? I'll put more questions on linear algebra in the handout. Maybe I'll introduce a section where if there's no time to take another session, then maybe I'll put something that has to do with rank, etc. And maybe also put problems based on that in the handout. Okay. I guess we can stop recording.
Sorry, just a second. It does not seem to